Youssry, and I'm gonna give you a little bit of a background. His short bio. So Akram did his bachelor and master in Egypt at Ain Shams University in Cairo between 2012 to 2009, I guess, and 2015. And then he did his PhD at UTS. He finished and in 2021, end of 2020, and then he joined RMIT in my group since 2021. And his work lies at the intersection between theory and experiments. So his theorists call him an experimentalist now, and experimentalists call him a theorist, a bit like me. So the title of this talk is Graybox Approach to Quantum Control. And thank you, Akram.
Thanks, Alberto, very much for the introduction, and thanks everyone for joining us today. So I'm going to talk about the Graybox approach to quantum control and try to give an overview of what we've been doing in the past 4 to 5 years. So yeah, let's start. So I want to start with talking about what we do in quantum engineering. So we usually have an idea for a device, and we try to do a design for this device which looks like ideal with perfect geometry and perfect materials and everything. And we have some idea, yeah, we can uh, uh, design this device, and then we go to fabrication. And once we start the fabrication, then there will be like a difference in the behavior between the fabricated device and the ideal one, because we cannot have like these nice geometric features and sharp edges and everything. So the fabrication errors will cause deviation in the behavior of the device. We also have some things that are difficult to account for beforehand, things like noise, for example. We don't know beforehand what kind of noise would affect the system. And we also have some engineering limitations that come from the equipment that we use, like the microwave generators, the lasers, the power meters, all of the other equipment that we use to operate the device. And so what we need to do is to do some sort of identification. So we have our device, we go to the lab, we perform some measurements, plot the points, and then we fit a curve. This is like the standard thing to do. So we're going to talk about identification more details shortly. And the purpose here is to try to understand the actual behavior of the fabricated device versus the ideal one that we started with. And then comes the next stage, which is controllability. So controllability is a theoretical study which aims to answer questions like what kind of gates, for example, quantum gates, I can implement with my device in the presence of limitations. So if, for example, I have some control voltages, if these voltages are limited to some range, can I implement everything, all gates, or there's only a subset that I can do? And this is in general a difficult question. And so it's still like largely an open area of research. The next thing is control. So I want my device to have some target. For example, I want to implement a quantum gate, and I want to design my controls to have so that the device like implements this target. So this is the last stage. Well, what we need to do actually is to have this in a sort of a cycle. So we shouldn't stop at one stage. This should be continuous cycle. So you'll find, for example, in noise spectroscopy in the literature, noise spectroscopy is the process of identifying noise in a quantum system. Find like the majority of papers will stop at the identification stage. So you know, okay, this is the noise in your system. But then you don't use this information to design better pulses, which is the control, for example. Or even if you do control, you stop here. You say, yeah, my device is working, but how to use the information that you learned after controlling the device and and seeing the actual performance. How can you use this information to design better devices in the next generation? So what we need to do is actually like think about this as a cycle, not just a one directional flow. So let's talk more about identification. So i- it's nice to have this picture here. So we have a simulator. What is a simulator? It's just a piece of software on your computer that simulates a device. Okay, so you give it as an abstraction, you give it some controls, and the simulator solves some complicated physics and give you some estimates for observables, like anything you can measure in the experiment. So this is like a simulator. So this is one side of the picture, and then you have the actual device, the one that you fabricated. So you have experiment. This is the actual thing, and so what happens? Yeah, you go to the lab, you apply some control, and you actually measure. Now, the question is, does these two, like, ideally, we need these two to be equivalent, like the same. But definitely, it's difficult to simulate everything. There are some things that we don't have enough information about. And so, having a simulator that accounts for every single effect that could happen is really difficult. And so, what we can do is we can have a third picture, which is the machine learning. So what we can do is we take the measurements we have from the device and then train a machine learning model so that it predicts the observables, the outcomes, what I can measure from the experiment. And then we have these three pictures to have in mind that ideally we want the simulator to be as close as possible to our experiment, but this is very difficult. And so instead, we use data collected from the experiment and use machine learning to find a model that is as close as possible to the experiment. Once I have this machine learning model, then I can use it as a replacement for my device and like as a better simulator. And so how do we do this? How do we use machine learning to find such a model? Well, there are three approaches. So the first approach is what we call a white box, which is like the standard curve fitting, we can say. Like you just have some physics laws that you know that they are correct, and you try to fit some unknown parameters. Like for example, in some device, the Hamiltonian depends linearly on voltages. And so you do measurements and then you try to find the constants of proportionality. And then you know everything. So this gives you everything, like all the physics. But this works if you know the physics beforehand, okay? If there are some parts that are unknown, then your model will not be accurate. And so the second approach would be to use standard machine learning, like uh, the classical way to do it, which is what we call the black box approach. So in this case, what's a black box? It's just something like a neural network. What's a neural network? It's just a composition of nonlinear functions. So you always see these pictures of neural networks. Mathematically, they are nothing more than just hyperbolic tangents and like other nonlinear functions. So why neural networks work? Because there is something called the universal approximation theorem. So there is a theorem that says if you have like a map between two compact spaces, then there exists a neural network that will approximate this map up to your desired accuracy. And so this is why it works perfectly in all classical applications. But unfortunately, this doesn't give you any physics because you're just abstracting things away so that the machine like fits the data, but there is no physics. And this is like traditional machine learning. When you want to write a software to classify the pictures of dogs versus cats, there is no equation that describes dogs and cats. You don't need any physics there. So this is like why machine learning was designed in the first place in this like abstraction. You just want to solve the task. In in uh, in our applications where we want to understand physics, this might be a problem. because we don't a neural network wouldn't understand the concept of Hamiltonians and unitaries and all of these things that we have in quantum. However, this might be useful in some applications, like if you only care about, for example, controlling outputs of the neural network, then this would work. But if you want to access something hidden, some object, some quantum objects, some operators, things that are like physics related, then this would be difficult to use. Okay. Um, then okay, so then we can merge these two directions together, and then we get our gray box approach. So what we do here is we split things. So parts of our model that we are 100% sure about, we implement as white boxes. For example, if I have a Hamiltonian, I can calculate the unitary and solve just solve Schrödinger equation. If I want to calculate probabilities, I use Born's rule. So whatever physics laws that are there that we know that they are correct, we just use them in the white part of this gray box. And then remains the things that we are not sure about. Like the Hamiltonian depends linearly on voltage. Does it really depend linearly? Maybe it's quadratic, like who knows? So when you have things that you are uncertain about, then in this part of the model, you put your black box. You put, for example, here a neural network. And so the combination of these two things, neural networks and white box layers, this forms a gray box. And the cool thing about it is that you control how much detail you need. Like maybe in one application, you just need to know your unitary as function of controls. Then you don't need to go and know the Hamiltonian. You don't care. You just need the unitary. In other application, maybe you need the Hamiltonian itself. So then you add a layer that will estimate your Hamiltonian. So how much you put there and in the white box and how much you hide inside the neural network depends on your application. So the gray box, by the way, like has been in the literature for classical control engineering for a long time. We were first to do it in the quantum applications around 2018 because it's actually like it's difficult to do these things. This at the end, this is a software, so we need to do like back propagation and calculate gradients and stuff. And when you have quantum mechanics with time-ordered evolutions and complex numbers and all of this complicated math, it was difficult actually to implement like a gray box for quantum applications. Around 2018, like when we started working on this, Google TensorFlow was like starting to emerge, and other like software tools, which actually allowed us to implement these ideas in uh, in software. Um, okay, so I have my model. How can I use it for control? Remember this picture we had before that now we have a machine learning model that replaces your device. So you can just do like standard optimization. Like the model now will give you all the information you need. And so you can form like a cost function, uh, which is like just measuring the difference between the predictions of the model and your target, and then feed this to any kind of optimizer you want, and then you design the pulses that you need. Uh, and So here the use of the gray box would be useful because it gives you all the physical quantities you need to the level of details that is required. Like for example, to do control, I need the Hamiltonian as a function, the Hamiltonian as a function of control of the pulses, of the input pulses. I need noise operators. Like these things I can actually estimate from my gray box, and then I can form whatever cost function I need for my application. And then I do optimization. So this actually will remind you with grape, for example, the grape algorithm, which is like a very famous technique in quantum control. So this is actually related. It's the difference is like Grape is either you do it on a simulator, so if your simulator is not close to the actual device, then you will not get very good pulses. Or you do like online Grape, like you actually execute the Grape algorithm on your device directly. And this is like uh, challenging because you have to keep updating the pulses and measuring. You have to put it in a loop. And then what we are proposing here is, okay, replace the experiment with a machine learning model and work offline on your computer. So what have we been doing the last 5 years? As I mentioned, we started in 2018, uh, and here we were studying like a photonic system. So photons don't interact with together. So it was like a unitary evolution. There was like we modeled it without noise, and the Hamiltonian is time independent. And we were looking into like the control of some semi-classical effects that we have in these systems. 2019, we started extending this from like closed system to open quantum systems. So when we have noise, and we are focusing on the characterization step more than the control aspects. In 2020, we used the idea again for the Graybox in a different application, which is noise detection. We have a spectator, like an extra sensor, quantum sensor, where you can sense the environment and say information about the noise. And then in 2021, we did actually an experimental implementation. So we did implement the Graybox on a photonic system in experiments, so not just in theory. And I'm going to look in this more detail. And the last thing we had very recently is control, like a theory work where we control a qubit in an unknown non-Markovian quantum pattern. And I'm going to talk about this also in some detail. Um, okay, so let's start with this work here. So we had this kind of device. So it's an integrated photonic circuit, and we have these coupled waveguides, and we have these electrodes. And when you apply electric fields on these electrodes, this material, it's called lithium niobate, you can control its optical properties like a refractive index and stuff by changing the voltage. And so you can control the propagation of your light through the chip. Uh, and so what we don't know, what's the unknown here, is how the voltage will change the Hamiltonian that describes the chip. So for example, people like say, okay, it has some structure, some tridiagonal form, but maybe this is not true. Like maybe it's something different. And we actually, like in the initial experiments, we found that the usual models do not fit the actual fabricated device. And so the protocol that we use, which applies to any experiment, not necessarily this optical device, is as follows. You start by creating a data set. So what is a data set? It's just uh, a collection of pairs of inputs and outputs. So what are the inputs here? The voltages. These are my controls. So I go apply some control voltages on the device, and then I have a laser that's propagating, and I measure the output power distribution of the laser at the output of the device. And I repeat this for different voltages. I do measurements, and this is my data set. And then what I do, I fit a gray box model. I train the model. So what's training? I want to minimize the error of the prediction. I want my model to produce correct prediction. So I form a cost function and I minimize the error over the neural networks that we have inside the gray box. And then the third step would be to test the model. We need to know that um, the model can predict measurements, like new measurements. So it will be bad if your model only memorizes like the training data set. The model should be able to predict measurements if you have new inputs. Okay, so we test this as well, and then we can do control. So once I have my gray box, I can design control. So I want to find the voltages that would create some desired distribution, power distribution, or some desired unitary. And then we test. This is the important thing. We test experimentally these pulses. Okay. And so this example of the results we have here. So on the upper panel here, we have a histogram the of like of the counts of the gates. So here we had 1,000 targets, and we are counting like the percentages of fidelity. So for example, how many how many of these 1,000 targets had 90% fidelity, how many got 94% fidelity, how many got something like near 99% fidelity, and so on. So this is just a histogram of the counts. So here we are comparing a gray box, uh, a white box based on the known physics, and a black box, which is just a neural network. And we can see here that for the black box and the white and the black box and the gray box, the counts for the fidelities that are high, like above 99%, is very high. Okay, so this means that when you want to do the control to find like the power to have a target power distribution, both the gray box and the black box perform well. The white box is not performing good because there is some physics missing there. Now, if you want your target to be unitaries instead of power distributions, then we cannot use a black box, as I mentioned, because there is no physics. I cannot ask a neural network to give me a unitary. It doesn't know what a unitary is. And so we can only compare gray box and white box. And we can see here that the gray box outperforms the white box. Um, then the bottom panel here is the MSE. So MSE is the mean square error. This is like the metric we use to assess the performance of machine learning models. So we are also comparing the three methods, and the first part here is for the training data set. So ideally, I want the MSE to be 0, like that the model is perfect. So the smaller the MSE, the better uh, the model is. So we can see here again for training and testing data sets, uh, both uh, the gray box and the black box perform nicely. The white box is far. And in terms of control, we see here this is the same information here, but with a different metric essentially. So when I have a power distribution control, then both the gray box and the black box perform well, whereas when I have unitary control, I cannot even use a black box. So this is like very interesting results because this is actually an experimental demonstration. Like these are not just simulations. This was done on an actual device, and we actually did learn some of the like some new features of the device, some physics by fitting the gray box model, because now we can probe the Hamiltonian and see, okay, this Hamiltonian is different from the one that's commonly used, and we learned more about the device uh, using this gray box approach. Um, the next thing I want to talk about is, okay, this photonic device was like a unitary evolution. What happens if we have like an open quantum system? We have non-unitary evolution. So we started this work back in 2019, and here we use the following idea. So usually if I want to write the Hamiltonian of an open quantum system, we split it into two parts. So the first part is the control, like for example, you have a qubit, you have some drift term, and then you have your pulses. And then you have a noise term in the Hamiltonian. So here I'm showing an example of what a noise term would be. So you'll have this is the classical noise. So these betas are classical stochastic processes. And so like these terms are stochastic, okay? And so this represents noise. Uh, so um, turns out that we can write down the expectation of any observable we want at some time after evolution in this form. So what we have here is, if you notice here, you have you control rho at time t equals 0, you control dagger. So this part here, these three terms, is nothing more than the evolved state at time t capital. So this is just evolving the state. This is the rules of quantum mechanics. And then you have the trace of the evolved state times the observable. So this is just calculating expectations. So the only extra thing we have here is this operator here. This is VO operator. So this noise operator is actually a system operator, so it acts on your system. And so this is very cool because uh, if your environment is not classical, as this example, if it was a quantum environment, then this quantum environment would be like described with like an infinite dimensional space, and it becomes very complicated to work with these objects. So it turns out, and we had like there is a rigorous proof that we can always write this expectation in this form, that we have this extra system operator here that accounts for everything about the noise. Okay. And the nice thing is that it doesn't depend on any assumptions or approximations or anything. You can always write this exactly. Now, if you want to write this VO like in an analytical formula as a function of your controls, then it's difficult. You'll have to do approximations and things. But in general, you don't like uh, this formulation in itself is exact. Okay. And also like this operator, like with this kind of formulation, we don't care about the environment. Is it classical? Is it quantum? Is it Markovian, non-Markovian? We don't care. We just all the effects that deviate from the unitary evolution is just encoded in this operator. And so we can do all the tasks. Like if I want to do dynamical decoupling, if I want to cancel noise, then I can write an optimization problem where I want this VO to be identity and the evolution of the state to be the identity map. So the state remains. So this is like a quantum memory. If I want to perform like a quantum gate, then I also want to cancel the noise. So I want this VO to be identity, and I want the evolution of my state to be the desired evolution. And um, if I want to do noise spectroscopy, like understanding the noise, the environment, I can also like work with this VO and estimate like the spectral properties and so on. So this provides like a complete framework for doing things. So the question is, okay, this is theoretical. How do I calculate this operator in an or for an actual device? Okay, so here we use the Graybox. So the idea is, okay, I know how to calculate uh, the U control. This is just the pulses I'm applying, the evolution of the pulses. So this is something I can calculate. I know rho, I know the observable. So all of these things I can put in a white box. Okay. Now for the VO, I just want to calculate it as a function of the pulses. I don't need an analytical formula. I just want something to calculate it. So I can put here a black box, and then the combination will give me the gray box. Okay. And so this is how it looks like. So I take the pulses and I pass it to a black box, some neural networks, and this here would estimate my VO. And then the other part will take the pulses and calculate the control Hamiltonian and the unitary. And then at the end, I do the measurement. So all of these things are the white part here, and the black box part here is for calculating this VO. And when I train the model, these are the same steps that I just described before. So I create a data set and I train the model, and then this acts as a replacement for the device. It's like a simulator for the device that is like reversed engineered based on the measurements that I have experimented. So so far this is like we haven't this was just like theoretical work. We are currently working on applying it experimentally with other groups in CQC2T. Uh, but yeah, this is actually like a nice way to work with open quantum systems. So so here I mentioned like, okay, I need to create data set. So what I want to talk about next is, okay, talking about like research methodology. If I want to work on quantum control and I don't have access to a hardware platform, I'm still developing methods. So what do I do to create these data sets? Well, uh, we just simulate a quantum system. So how do you simulate a quantum system? Well, if it's closed, you just solve Schrödinger equation. That's it. Or use the Liouville's equations, also called von Neumann's equation. It's just like the same Schrödinger equation written in terms of the density matrix. So you have some Hamiltonian, you solve the Schrödinger equation, you get the evolved state, you can calculate observables. Okay, if you have an open system, open quantum system and your noise is classical. How do you do it? You do a Monte Carlo simulation. So you have this stochastic term in the Hamiltonian. So you generate different realizations of the noise process. For each realization, you solve the Schrodinger equation, and then you average over all this noise realization. And this works for Markovian and non-Markovian classical noise. So Markovian will be like just white noise, non-Markovian will be colored noise. And this is actually like very time consuming. Like you can check this paper we had. We created data sets on a supercomputer and we ran it for like 6 months with GPUs and like everything, because this is very slow simulation, even for just a single qubit. Uh, and so like in some situations, doing the experiment is faster than simulating it on a computer, actually. The next thing is, okay, if you have an open quantum system with Markovian quantum noise, so your environment is quantum, what do you do? Well, you solve a master equation. So it looks like this. It's similar to Schrodinger equation, but then you have an extra term here. This is the dissipation terms. Uh, then the last thing, what happens if your noise is non-Markovian? This is like more difficult. Well, that turns out there's a trick actually you can do. So what it is, you introduce an auxiliary system. So you have your main system, like a qubit, okay? You want to simulate non-Markovian quantum noise. So you add an extra system, an auxiliary system, and you solve a master equation for the system plus auxiliary. So you're assuming that system plus auxiliary, this combined system evolves like in a Markovian evolution, and then you trace out this auxiliary after the evolution. So what remains is the evolved qubit of the main system, and this would be non-Markovian. You cannot write it as a master equation. And so we use this trick in our most recent work. So we studied like fermionic and bosonic paths. So this is what I was saying. So you have your qubit, you add this auxiliary system, and then you couple this to your environment and solve the master equation. So here you have like the standard control Hamiltonian for your qubits, and then you have your coupling terms to this auxiliary system. So the A and A dagger here is like bosonic creation and annihilation operators. And so this gives you like a way to simulate non-Markovian quantum paths. Um, so this is an example of the dynamics. Like, what does this evolution look like? So on the upper panel here, we have the expectations of the states, like the expectation sigma x, sigma y, and sigma z, the three Paulis, for different states, like different eigenstates of Paulis. So the first two plots here reminds you of the Rabi oscillations. It's very similar. So you have your, if you start with the x plus state, it there you have the oscillations that decay over time. The interesting thing here is when you look at uh, the expectation of Z for the zero, the ket zero and ket one, like the North Pole and South Pole of the block sphere. You can see here that first of all they are not symmetric. Like the evolution of these two states is not symmetric, and there is actual evolution. Like even if you start with the ground state of your qubit, it will decohere and then it goes towards a mixed state. So this is really like this is some interesting dynamics for this model. It's not like the usual T-phasing. If you have a usual T-phasing model, then the Z states are eigenstates, so they don't change. They will remain constant. They won't change. That bottom panel here is studying the effect of this V. So you can see here that when we increase the V, it becomes like this purity. So trace rho squared. So the purity of the state. So you see that when you increase V, the purity goes down. So purity of 1 means a pure state, purity of 0.5 means a completely mixed state. So over time, you are losing the purity of the state. And you can see it actually doesn't just go down, it goes down and then goes up. And like, there's some kind of oscillations. So the dynamics are like interesting for this model. And so we did the same steps here that we create like a data set, and then we use the Graybox. And then we focus in this work actually on the control aspects. Okay, so we had like this universal set of gates like Pauli's identity, Hadamard, and the rotation. And we did some comparisons and studied the performance. And so the key results we found is that, first of all, that multi-axis control is way better than single-axis control. So if you have a closed system, from the basic controllability, like the Lie algebra, if you have a drift along Z and control along X, this is sufficient to produce everything. But turns out if you have like an open quantum systems and your pulses are constrained, this is not true anymore. And so we found that actually adding this extra axis, so like you do control in X and Y, actually performs better. The next thing is that the control constraints are really significant. So if your pulses are very limited in power, there is so much you can do. Like it affects the performance greatly. If your pulses are very strong, if you have strong, like the power of the pulses are strong, then you can overcome the noise easier. Okay. And so this reminds us again with controllability. Like with the Graybox, you can focus on studying these aspects of systems, focusing on the control rather than okay how I'm going to simulate the system. Now you have something that's driven from an actual device. What else? Yeah. So another result here is that increasing decoupling, like this how much the system is coupled to this auxiliary. This coupling strength will also affect your like how much you can control. So this parameter corresponds to how strong the noise is. So the stronger the noise is, the more difficult it is to control the gates under constraints. Another thing is the choice of the cost function when you do the optimization for the pulses. This is very critical. Like we tried different cost functions and we found like there are ones that perform better than the others. And again, so with the use of the gray box gives you all the information you need. And so you can just focus on control. You just take these quantities, noise operators, unitaries, Hamiltonians, and then you design your cost function and then study them. So this is only possible when you have like this architecture for the gray box. We studied also other things like finite sampling and how we do the optimization for the control, but they're like the results here were somehow inconclusive about the effects. So the most significant things is the control constraints in relation to the strength of the noise. Okay. And so, yeah, so the conclusion here is that, yeah, the gray box is very useful, really, to study open quantum systems. Okay. Um, okay, so to sum up what I've talked about today, we talked about this quantum engineering cycle. So you start with design, fabrication, and then you do identification, controllability, and then control. For identification, you can do like a white box. If you know everything about the physics, then just use a white box. The other thing you can use is black box, no physics, and this is good for some applications where you just need to have output control. And then the gray box, and you can control how much in the gray box, how much detail you want. And this is like the combination of these two approaches. I showed some of our recent results. So we have uh, experimentally demonstrated this for a closed quantum system, this approach on our photonic chips we have in our lab. And we did an extensive theoretical study for the case where we have like a quantum system with unknown non-Markovian quantum noise. So that the nice thing here is that I don't need to learn everything about the environment, which would be very difficult. I just need to know the effect of the environment on my system. And I don't need to know beforehand anything about the environment. With this gray box approach, I just train it with experimental data and that's it. I don't need to know any assumptions about the noise at all. So this is actually pretty useful. Um, So what are the challenges we have in this approach? Well, we inherit all the problems and challenges of quantum mechanics and machine learning. So, for example, it will be difficult to use this approach to characterize a system of 100 qubits because I cannot even write a state of 100 qubits on a piece of paper. It's impossible. So these kinds of problems that we have from quantum mechanics and machine learning will be there in this approach. So what I think, like the perspective here is that we use this approach in NISQ devices. It's more useful in the NISQ era where we have like small number of qubits, so we don't have the problems of the exponential explosion of information. And so this could be very useful actually for like current state of the technology right now. And so we are looking forward to collaborate with all CQCT2T groups, and this like collaboration is very important for developing both theory and experiment. So when we actually did implement this approach experimentally, we learned a lot about the performance of the method itself. And also we learned about our device. So this is very useful for both doing theory and experiment. So please talk to us anytime. We're very happy to collaborate with everyone. And so the final thing I want to say is like the take-home message here um, is if you are doing like if you're doing theory, you get a Graybox. If you're doing experiment, you can use Graybox. If you're doing both like me, then you also do Graybox. Everyone gets a Graybox. Thank you.
Thank you, Akram. Nice
Thanks.
talk. We all get a gray box then. Um, I'd like to ask from the audience if anyone has questions, maybe raise your hands. Okay, maybe I'll start while people decide what questions they want to ask. Let's talk about cost functions.
Yes.
So with the cost, so the cost function needs to be selected for a specific problem.
Yes.
And so here you presented a range of different systems, you
Yeah.
know, time dependent, time independent, open, close, Markovian, noise,
Yeah.
non-Markovian, and more potentially. How does the optimal, well, so how do we define optimal cost function, and then how does it change for the different type of problems? If you have an experience, maybe there is no like a definitive proof, but like what
Yeah.
is the other takeaway from this?
So yeah, I think in general, this is like finding the right cost function is a big part of doing the research in quantum control. So for example, here, if you want to do like say dynamical decoupling, so a quantum memory, okay? So here you have two objectives. So the first objective is you want this VO operator to be identity, okay? So this is one objective. The other one is you want your state to evolve, like to have an identity map evolution, okay? So these are two objectives, and in fact, like I'm just hiding some details here. So this VO, like this O is an observable. We need to satisfy this condition for the three Paulis. So like V sigma X, V sigma Y, V sigma Z. And so in fact, this is a four objective problem. And so this is actually like what can happen is that when you are doing the optimization, they can be contradicting with each other. So maybe the pulses that will cancel the noise in X direction are not very good to canceling the noise in Y direction. Okay. And so this in itself is like, yeah, it's a challenge. How do you find the best cost function so that because we have different conflicting objectives. Okay. But the cool thing about the gray box is that you have the information. So we can now focus on these aspects. Okay. I like I have a device with some unknown noise. I don't know what is it. I train my gray box with data driven from the experiment, and then I replace the experiment with this machine learning model, this Graybox model, and it gives me all the information I need. Now, as a researcher in quantum control, I can just focus on this task, because the problem when we do like just general quantum control research is that we start with some simulator, but there is no guarantee that like this simulator matches what the actual device. And then I design things and I get pulses that are good for the simulator, but they are not good for the device. Okay. So here what I'm like the message is that once you train the gray box, you can now focus all your research on control. You just do that you train the model in the beginning and forget about everything else and then just focus on what you can do now in terms of control. So yeah, so I think this answers the question hopefully.
Any questions from the audience? So I'll just ask a second question, and then if we don't have anything, we just wrap up.
Okay.
So in terms of the other standard control techniques, you know, um, or pulse selection protocols, and you know, grape, or you have
Yeah.
dynamical decoupling for certain applications. So you know, they are commonly used. Many traditional methods, well-known methods, are commonly used, and we can see sort of high fidelities, implementations of gates, etc. So why do we actually when do we actually need a better technique? At which point?
So you can see here, for example, like this is an open quantum system with non-Markovian quantum buck, okay? So it turns out if this coupling, for example, here is very small, you see that the evolution, the purity stays almost close to one.
Mhm.
So it is open, like technically, yeah, it's an open quantum system, but effectively it's like evolving very close to the edge of the Bloch sphere that you can almost consider it closed. Like the noise is not that strong. So in this kind of weak coupling regime, if you apply like standard techniques, you'll get high performance. Okay, because it's almost like it's almost closed. Whereas if you have like stronger noise, as like you can see here, then the qubit, like the purity here, it goes at some point to like 0.6. So it's like it's about to be you are about to lose your qubit actually. So in this kind of regime, the standard techniques would not would not work. So and actually, so for example, also if you think about grape, the idea of grape is optimizing the fidelity between the output and your target. So if you want to do this on a system with non-Markovian quantum body, it's actually very difficult because like you need to simulate this thing continuously with every iteration of your optimization. Using a Graybox is more efficient because it's just a bunch of neural networks, and with the software tools we have, TensorFlow and GPUs and things like that, it becomes more efficient actually. So, so I'd say that yeah, in some experimental platforms, maybe the noise is not strong enough to cause like very different behavior from a closed system, and then the techniques will just work. For other systems, yeah, it will be more difficult. And
Or
that
maybe they are too slow, too
yeah,
small to be challenging the conventional techniques.
yeah.
Yeah, yeah. So at some
So
point they
another
will fail.
so another thing would also be if you like the things could work for a single qubit, but if you have two qubits, for example, it will be difficult because there's cross coupling and there's other effects that then you start to see that the conventional techniques wouldn't work. So this approach works for any finite dimensional system. So we can use that idea instead of having a qubit, you can have two qubits, for example. It would still work.
Okay, thank you, thank you. I don't see any hands. Nobody have questions, so I think we're gonna wrap up. And please join me and thank Akram again for the fantastic talk. And anyone who has interest in working on this with us, welcome. Just talk to us. And yeah, we went maybe 15 minutes over time from the initial planning, but I think we did pretty good. Thank you again, Akram, and thanks,
Thank you.
Alison, Rosanna, and the team for organizing. And see you everyone in the next series, next event of this series.
Thank you both very much. Thanks, everyone.
Thanks very much. Thank you.
Thank you. Bye bye.
Bye.